Hey everyone, my name is Taylor Sparks, Editor-in-Chief of Integrating Materials and Manufacturing Innovation, with a brand new paper to talk about. This is all about defects in laser powder bed fusion. Specifically, we're looking at Inconel 718, and we're looking at stochastic lack of fusion defects. This work comes to us from various researchers, Caglar Oskay's group at Vanderbilt University, but also with researchers at NASA, University of St. Thomas, and Analytical Mechanics Associates. So what are these lack of fusion defects? Laser powder bed fusion is a fantastic technique. It has a lot of things going for it, but it does have some problems. It says here a critical challenge is the analysis of process-induced porosity, things like gas porosity, keyhole porosity, or lack of fusion defects. And there's been quite a bit of work on this showing that these exist, specifically here in this paper on Inconel 718 by Kumar and coworkers, where they point out that there is a statistical nature to the defects that exist for these lack of fusion defects in these materials. Furthermore, there's been quite a bit of lack of fusion modeling done. For example, this paper by Tang, where they're specifically looking at the impact of local undermelting in causing these lack of fusions. Now, what's interesting about this paper, and a key part of their hypothesis, is that these are stochastic defects. You don't expect them to happen in the region where you're operating, but you do still. So what's going on here? They point out that there are multiple different phenomena that govern melt-pool dynamics, and these can couple strongly with each other, resulting in experimental scan tracks that have larger fluctuations than you might expect. So what are they going to do? They're going to build a data-informed approach for predicting these defects in these materials. They're going to compare that to direct experimental observations. To do that, they have a spectral matching algorithm that's going to help them actually reproduce these fluctuations to look for them. They're going to use this data interfaced with a VBLOF open source model then to generate realizations of these types of defects using Monte Carlo sampling. So maybe let's start by taking a look at the actual scan tracks to see this variability in say, the melt pool depth. Here you see for a single sample, here it's tracking the melt pool conditions. Here you can see the melt pool depth. And then for multiple different tracks, take a look at this. On these 5 tracks, the huge variation, the fluctuations that you can see on these scan tracks next to each other. Using their approach, they're then able to actually predict the volume fraction of defects and compare that to the volumetric energy density. And you see that comparing simulation to actual experimental conditions, it matches pretty well. So ultimately, they're able to generate these types of analyses of predicting lack of fusion defects. And they're able to predict and observe a decrease in the coefficient of variation for the volume fraction of these defects as you begin to approach the nominally fully dense region. But they can also generate these sort of cumulative distributions, as you see here, of defect morphology. And note that the presence of these sort of extended tails suggests that even though there's a low probability of finding these lack of, sort of large defects far from the mean, you can still find them. That it's not zero, right? They can still exist. In fact, they were able to go back to that analysis by Tang in 2017 and identify regions in your processing conditions that will lead to suboptimal conditions in terms of creating stochastic defects. So check it out in the latest issue of IMMI.